Sorry, the session had ended, maybe again the internet fluctuation, but okay, we'll start from where we stopped. Okay. So, yeah, I hope it's getting shared. This, yeah, we were discussing this soap bubble 1, soap bubble 2, this is the resultant and in which direction the air will flow. So we know that at contact region, and they are communicating with each other. Okay, so the thing is, let's calculate the excess pressure. So the excess pressure inside soap bubble 1 will be, let's call it excess pressure, let's call it P1. For this soap bubble 1, the excess pressure will be 4T by R. Let's call this R1, and the excess pressure for soap bubble 2 will be 4T, because it's the same soap material, so surface tension value will be same, but the radius is different. So this is the excess pressure corresponding to soap bubble 1, and this is for the soap bubble 2. Now since we are seeing that excess pressure is inversely proportional to the radius, so if the radius of bubble 1 is more, that means the excess pressure will be less for it. Okay, whereas if the radius is smaller, the excess pressure will be more. So what will be the net excess pressure for this kind of situation? The net excess pressure for this kind of shape of bubble, let's denote it something like this. I mean, the surface tension will be same, only the radius now of this shape has changed. Let's call it R final. Yeah. So actually we don't, okay, sorry, we don't need to calculate this also. We just need to tell this, right, that what will happen. So since we know that excess pressure is inversely proportional to the radius of the system, here the radius is different for these two soap bubbles, so that means excess pressure will be more when the radius is small, right? From this relation, if R is small, excess pressure will be more, so the excess pressure will be more inside the, that means excess pressure will be more inside, P2 will be more than P1, right? If we are considering that soap bubble 2 is smaller than soap bubble 1, that means R2 is less than R1, that means P2 is more than P1, that means the excess pressure inside soap bubble 2 is more than the excess pressure inside soap bubble 1. Is there some sound? Is everything alright? Yeah. Okay. Everything is fine. So yeah, so there is more pressure inside the smaller soap bubble. So which one is the correct statement? So yeah, what this means is, if there is excess pressure inside small soap bubble and there is less pressure inside the bigger soap bubble, this is excess pressure, here is P1, here is P2. Since P2 is more than P1, that means the pressure will flow from the soap bubble 2 to soap bubble 1, and it will keep on increasing. So air will flow from smaller into larger one, and larger bubble grows at the expense of the smaller one. So until the pressure becomes equal, this pressure will keep on flowing from smaller to bigger bubble until the pressure between these two becomes equal. So the correct statement is C. This is what will happen in this situation. Okay. Okay. Now this we did. Now another question. So here we have two soap bubbles of different radii again. One soap bubble has radius capital R, another soap bubble has radius small r, and we have given this relation that r is more than the radius of this small bubble are touching each other. Okay, they are again touching each other. We have been told they are touching each other. The radius of curvature of the common surface at the region of contact is, so at the region of contact, again it's similar, we can understand. Say this is the capital one, this is the small one, and we would need to find out the common surface. This is the common surface. What is the radius of curvature of the common surface? What will be the radius of this common surface? So we'll find out the excess pressure inside this soap bubble and then inside this soap bubble, and then we'll understand what will be the radius of this common surface. So for the big bubble, for the resultant at the contact region, the radius of curvature of soap film will be taken care of by the net excess pressure, and the final will be 4T by, let's call that radius of curvature, let's call it R prime. So the final will be this, which will be the difference in these two. Now we know that the smaller one will have more excess pressure, right? Since we know the relation P is 4T by R, and smaller the value of radius, higher is the value of excess pressure. So this minus this will give us the resultant excess pressure in the resultant shape. So 4 will get cancelled, T also will get cancelled. We will be left with 1 over R prime is equal to 1 over R minus 1 over capital R. So we R minus R, and when we'll take reciprocal, we'll get R minus R. Okay. That means this is our correct answer. So the radius of curvature of common surface of region of contact will be this. This is the correct answer. Okay. Now the next question. The surface tension of soap bubble is 0.04 Newton per meter. The energy required to increase its volume from 2 pi by 3 to 256 pi by 3 centimeter cube is. So surface tension, again we have here a soap bubble. We have a soap bubble whose surface tension value is 0.04 Newton per meter, and the energy required to increase its volume. So initial volume would be initial volume we have been given 32 pi by 3 centimeter cube. Final volume, we have given 256 pi by 3 centimeter cube. Energy required to increase its volume. So if the volume is increasing, means the surface area will also increase. and if the surface area will increase, there will be some work done, or there will be increase in the uh, increase in surface energy will increase. We need to find out that increase in surface energy. So uh, to be able to find out the value of surface area, we need the value of radius, and we don't have that. So with these volume, we will calculate the initial and final radius. So for this case, since we know volume is given by 4 by 3 pi, I'll denote initial radius as Ri. 4 by 3 pi r cube is 32 pi by 3 centimeter cube. So 3 cancel, pi cancel, 4 8, right? That means initial radius, I'll take cube of 8, that means 2 centimeter. Sorry, it will be 2 centimeter. Similarly, for this final volume, if I'll compare it with the formula 4 by 3 pi r, I'm calling it RF, final radius. So again, this pi cancel, this 4, 6 are 24, 4, 16. Okay. That means RF cube is 64 centimeter cube. It implies that RF value is 4 centimeter, right? Because cube of 4 will be 64. So we got that our initial value and our final value we have obtained. That means the increase in area increase in area be the surface area, or the area for a sphere is given by 2 pi r square. So 2 pi r square, this will be the surface area it's given by 4 pi r square. I'm sorry, it's given by 4 pi r square. Taking 4 pi common, it will be RF square minus RI square. The formula, substituting the value of RF and RI. So RF is 4 square, RI is 2 square. 4 pi times 4 square means 16, 2 square means 4. 16 minus 4 is 12. 4 pi times 12, from 4 is 48 pi, right? Pi centimeter square. This is the increase in the area. Now to find out the energy required to increase this, energy required, or we can call it work done, that will be the value of surface tension times this increase in area. Value of surface tension is given to be 0.04 Newton per meter. Okay, but the answers are in erg and joule. Okay, both. So we need to convert it, either everything we need to convert it in Newton meter, I mean the SI unit, or CGS unit. So area is in centimeter square. We can convert this surface tension, which is in Newton per meter, we'll convert it into CGS. So wait, first increase in area is 48 pi centimeter square. So the conversion of Newton per meter to, in SI unit it's Newton per meter, in CGS units it's dyne per centimeter, and we know that 1 Newton per meter, the relation we know, 1 Newton per meter is equal to 1000 dyne per centimeter. Yeah, it's 1000 dyne per centimeter. So if I'll convert this 0.04 Newton per meter to dyne per centimeter, it will become 10 to the power 3 means 40 dyne per centimeter times 48 pi. So the final answer, if I calculate, so 48 times 40 times, again I'll take the value of pi as 3.14, will be, I'm getting 6028.8. I'm getting 6028.8 centimeter, sorry, this is in CGS unit, means erg. Now it matches the best value here, it matches here is this. If I round off it and remove the decimal, it will be 6029 erg. So this is the correct answer. So this is the energy required to increase the volume of soap bubble from 32 pi by 3 to 256 pi by 3 centimeter cube. Because of this increase in volume, there will be increase in surface area, and thus there will be some work done, or there will be some increase in the energy, which we calculated here. Now the next question, it is about the capillary tube. So in a capillary tube, the fall of liquid happens when the angle of contact is. So again recalling back what we understood when we were discussing the theory of surface tension and capillary tube, rise of liquid in capillary tube. So imagine this is a capillary tube, and there are two ways the liquid can rise in it. Either the liquid can rise and make the concave shape, where here everything, this is the liquid and this is the atmosphere or the air. So this is called concave. The other way is this. And as we had discussed here, the liquid is there. Again, here is the air. This is that whatever liquid. This is that liquid. So either the case is this, here the surface tension acts like this, and the angle here is theta. The angle here that is made between, when we make tangent here, the tangent is made in this direction. The tangent is made between, the tangent to the surface, which is this direction, and tangent here, there is obtuse angle here. Here there is acute angle, but here there is obtuse angle. And this case happens when? This case happens for liquid like mercury and maybe some other liquid, but yeah, this happens for mercury, and this happens usually for liquid like water. So the question is, in a capillary tube, the fall of liquid happens when the angle of contact is. The fall of liquid, this is like rise of liquid, this is fall of liquid happens, or when in mercury you will keep, and if there are liquid, instead of rising outside also, what will happen if this is the container? If this is water and this is glass, the liquid will rise outside also like this. But if it is water, okay, outside also the liquid will rise like this. But if it is mercury, this is the capillary tube, then instead of rising, it will fall here. The liquid will fall near the surface of capillary tube. Here it will be flat and it will fall here. So the fall of liquid happens when the angle of contact between the surface and the tangential to this shape, when this is more than 90 degree. So it's less than 90 degree for concave shape, it's more than 90 degree for when the liquid is rising like this inside, and outside the shape is this. So the answer is 90 degree when it's obtuse. Okay, so these were the questions for based on these two experiments that we discussed in last week, which were based on determining the moment of inertia of flywheel. Where is the question of flywheel? Yeah, these were based on the moment of inertia of flywheel. We already discussed the theory in last week. This time we discussed the procedure, and then based on the working formula we calculated and did various problems. The same way, the another experiment that we discussed in this week's lecture were the experiment for measuring surface tension of a liquid. And in this interactive session we discussed what is surface tension and the capillary rise method that we use to determine or measure the surface tension of liquid in experimental lab. And based on this also again we carried out various questions. So this is what the summary for today's interactive session, and the time is also up. So the next week we'll be taking up the other experiments that will be discussed in this week's lecture.